All right. Uh, so hopefully, good morning. Hopefully you had a happy Thanksgiving. It's a tiny little taste of uh, of a holiday before the reading week. Today is the 14th. Now, assignment two is not due today. It is due on Thursday at midnight. I just have not updated the calendar. But otherwise, that's it. That's all we're worried about right now. There is a midterm coming up after the break. I will release a practice midterm probably today or tomorrow, and then you guys can yeah, use that to help you prepare. But yeah, otherwise, no tutorials due this week. Just the assignment. So yeah, questions. Yeah,
Um, well, there's like a GitHub and the files. Oh, I'm not, they weren't included in the
I think I gave. Yeah, I think I gave you like it. I just threw a make file that was an old one. So if you just make the changes,
changes are on the
yeah, yeah, you can use it as a template or whatever, but it's not, yeah, you wouldn't be using those commands. Yeah. Yeah, yeah. Also, did you guys get your assignment one marks back? Okay, I will follow up with Lars after I got a busy day. Sometime today, I'll follow up with Lars. That was supposed to be done. He had a couple left to track down, but they should be released. Anyway, I'll have that for you as well. All right. So yeah, any questions on the calendar? All right. So last class we were talking about linked lists, which not really exciting on their own, right? You've probably taken them before, but now we're viewing them again through the lens of encapsulation and memory management. And so we went through. There are, well, of course, a lot of technical details to a linked list. In particular, a singly linked list like this. So we went through some of the different cases and we managed to finish our add function. Okay, so our add function seems to be working okay. And during our in our add function, we of course have to make a new node, right? So again, the focus is going to be a lot on memory management. And of course, we had to make a new node in the list class because the node is private to the list class, and so no one else could actually even make a new node if they wanted to, unless we explicitly give them permission. Yeah, so that seems to work. We did some, oh, I think I have some, I think one of the things that we left off was, am I in the right place? B, might be in the wrong place here. No, I think there are some, oh, okay. There were some, just some print statements used to debug. I think at the end of last class, we had a little bug we were tracking down, but I guess I took them out. Okay, but anyway, we had a bunch of students and print them out. Everything seems to be working great. Of course, if I do val grind, that's not going to be great because we have a bunch of news and we don't have any deletes. But before we talk about the delete strategy as a whole, let's implement the remove function. So if we look at removal, there's two of them. We're going to just do this one. And so yeah, it returns a student pointer. We scope it in with the scope resolution operator. And there we go. Okay, so as with everything in a linked list, this involves a traversal. What I want to do is I want to walk through the linked list until I find the thing I want to remove and then remove it. So if we look at, and removing is just, just moving around some pointers. So let's do the most obvious case of remove, or like maybe the canonical case. We'll avoid the edge cases to start with. So let's say we want to remove from the middle, so I call remove B. And then, well, what I want to do is find where B is. So, and I'm going to make the safe assumption that I probably need a previous and current the same as before. So my current is going to point to head and the previous will point to null to start with. And then I say, well, is the current node pointing to a student with name B? And the answer to that is false. So I'm going to update previous and update current. And I'm going to say, is the current node pointing to a student with the name B? And the answer is yes. So this is the thing I actually want to remove. And to do that, I want to take this pointer here, which is the previous, and I want to point it to basically current arrow next. And that's enough to remove it from my list, at which point I can safely delete the node, right? Because again, the node is completely our responsibility. No one else has access to this. This is a private implementation detail of the list class. So I have to make sure I delete that. And then, well, the last thing I want to do is return this student, right? And so I'm gathering, you know, that is a clue from this function signature. I'm returning a pointer. So probably I don't want to delete the student. I want to return it. And in terms of error reporting, well, a natural assumption is also, if I can't find the student, I'm going to return a null pointer. And then whoever calls this function will have to check to make sure that this pointer points to something sensible. Okay. All right, so I wanted to do I want to do this. Let's initialize them, right? For safety's sake, previous equals null pointer. And then I want to do, well, a traversal, same as I always do. So while current is not equal to null pointer, and I will say previous equals current equals current next. Okay, so that's the machinery of this this function. And then, well, I want to check here. Before I advance my pointers, I want to check to see if the current is pointing to the thing I'm looking for. So I'll say something like, and let's, if, and now I want to see if the current data has this name. And so if I look at, well, I have an equals. I believe I said last class that it's probably better to use a getter here, just because it's more transparent. And I'm going to, right, if I have equals, this is kind of vague. Yes, I am using name here so that it does appear that I'm going to match according to name. But if I left out this, which I'm allowed to do, then all of a sudden it's, well, what am I supposed to put here? There's two possible strings I could use. There's number and name, or actually there's also major program. So which of them is it? So using, this is sort of like, you know, we're starting to get into design patterns. This is an abstraction layer, but it's in this case, it's one that we don't need and actually will obfuscate what we're trying to do. So let's be explicit. Let's just use a getter. There's nothing wrong with that. So if the current data get name equals name, well, that's the thing I want to remove, and I'm just going to break as before. So we're going to do the work to extract this thing outside of the while loop. Otherwise, we're going to keep going and possibly run off the end of the list, right? Maybe we don't find the thing we're looking for. Okay. So then we said, well, we just want to adjust this one pointer. So this, if we go back couple, this previous pointer, previous.next equals current.next. And that's all we really need to do. So previous next equals current, next. And now that current node is stitched out of the list. I want to return this student current data. All right, so current data returns a student pointer. Then I want to delete current and return the goner. Okay, and that should handle basically the remove from the middle case. Now, well, we did talk briefly, or I mentioned that at some point, if I don't find the thing I'm looking for, I'm just going to fall off the end of the list. And so when I exit this while loop, if my current pointer is pointing to null pointer, right? So I go to here and maybe I say, well, instead of remove B, I say remove D, or anything that's doesn't exist. Well, then I'm just going to keep walking and say, well, is D equal to B? The answer is no, so I'm going to update my pointers. And I say, is D equal to C? The answer is no, so I'm going to update my pointers. At which point current is pointing to null, and I just fall out the end of the list. Okay, so, well, while we're here, let's just do that check. So we're just going to do a quick, very explicit check. Say if current is equal to null pointer. That means we did not find the thing we're looking for. I just want to return null pointer. Right? That's the signal. That's something that we weren't able to remove this student for whatever reason. In this case, the reason is the student doesn't exist. Okay, so that should help with a bunch of stuff. Yeah, I guess before we get there, we can add a bunch more students and just confirm that everything works. And then we can start removing them. So yeah, everything seems to be good. Students are in alphabetical order. No seg faults or weird outputs. So I'm going to start removing some students. And to start with, we're going to remove somebody that doesn't exist. So we're going to test that first case where we checked to see if current is equal to null. So this should work. It should say removing Bob, but Bob not found, right? So down here, I do a null pointer check. If I did find Bob, I print him out and then delete him. But I should not actually find Bob. And so yeah, gone here. I guess I have a little error message somewhere. Where did I put that? Right there. Yeah, Bob not found. Again, no seg faults, no funny behavior. So so far so good. All right, let's remove somebody that does exist. If I look at this list, Tony is somewhere in the middle, so this should fit the case that we just did. So if I change the name to Tony, whoops, Tony and Zeke. Let's not do Zeke just yet. So we're going to do Tony. Tony, we should be able to remove Tony and then print it out. Tony should be gone. And of course, we allocated Tony in this main function, and when we remove him, right, we get that reference back, and then I better make sure to delete him, right? Again, this is my responsibility in the main function. And although, you know, as a rule of thumb, I say new here, then I should probably have a matching delete here. And if I don't, well, then I should know exactly why that is, right? I should have a good reason. Okay, so removing Tony. Tony is still there. Oh, that's a bummer. Who did I remove? Nobody. Oh, well, I didn't actually remove Tony, did I? That's weird. I want to do this. That would help a lot if I actually tried to remove Tony before I did that. Okay, so removing Tony, found Tony, printed out Tony, and then when we print out our new student list, Tony is not there anymore. Okay, so that seems to work. So it works if it's empty, it works if Tony's in the middle. Let's see if we get anything for free, right? Maybe this covers some cases that we didn't anticipate. So let's try and remove the last student. This, when we did add, this worked. So let's try it with remove. We didn't explicitly plan for this case, but maybe it just happens to work. Okay, so removing Zeke. Zeke was found and printed out, and then when we printed out the student list, Zeke was gone. So yeah, if we walked through the logic, you would see it's exactly the same thing as the add function, right? So when we remove, I say previous next equals current dot next. Well, if Zeke's the last person in the list, current next is pointing to null pointer. And so previous next points to null pointer, which is actually, that's exactly what I want, right? So if I want to remove this last element, and previous is pointing to here, and current is pointing to here, then I want previous next equals current next. That's going to point to null, and the last thing is going to drop off my list. Okay, so we got that for free. Questions so far? All right, so the last thing we want to do is remove somebody from the front. And that gave us trouble last time, so maybe it's a good bet that it's going to give us trouble this time. Do I have Amy down here? Amy's here. Well, we can remove Amy off the top. It shouldn't hurt if we try to remove Amy twice. We've already accounted for that. So the first thing we remove is going to be Amy, who actually does exist. She's right at the front. And removing Amy, we get a seg fault. Nice. Okay. Kind of expected that though. But let's quickly walk through that case, right? This is the exact same reasoning as what happened with the add. If I want to remove from the beginning, I say I have previous is equal to null, and I have current is equal to head, and I call remove A. And the first thing I do is I say, well, is the current thing pointing to the thing I'm looking for? And the answer is yes. It's a weird looking A, but all right. The answer is yes, and so I pop out of the while loop and I never update previous. All right, so the same with add. I might have this case where I exit the loop and previous was never updated, so it's pointing to null. So we can just explicitly look for that. So here, if current equals null pointer, return null pointer. If previous equals null pointer, well, then what do I got to do? I have to actually set my head to be, so I know my list is not empty, because otherwise I would have returned here. So I know there's at least one node in there, so I want, and current is pointing to it, I want head equals head next. And so that'll point to the next thing in my list. Maybe it'll point to null pointer, which is also fine, right? If I have one thing in my list, this is going to remove it. And then I think else we want to do this. And then the rest of this should be okay, I think. I don't know, let's try it out. Questions? All right. So, found Amy attempting to print. We managed to remove Amy. We didn't actually print out the list until down here, but when we did print out the list, we could see that Amy's no longer there. Okay, so these cases on the remove very closely follow what we did on the add, and we get the same sort of problems and the same sort of stuff for free. No linked lists in assignment 2. This is an assignment 3 data structure. I haven't quite decided what to do for assignment 3 yet, but it'll be some sort of linked list in there somewhere. All right, and I think if we then uncomment the rest of this, it should delete everything. And then print out an empty list at the bottom here. We still have Tommy. We didn't remove Tommy. Tommy. Forgot Tommy. We can take Tommy out here. Okay, printing empty list. We got an empty list. That's great. So yeah, everybody's removed. What's more, every time I removed a student, I deleted it. And inside my list, I deleted the node. So I should have no memory leaks also. All heap blocks were freed, no leaks are possible. No particular error messages either. That's nice. All right, so that's good. We cleaned up all our memory. At least we, in new, we had new node, or in add, we called new node, and then in remove, we called delete node. And that's a pretty good rule of thumb. Right, questions? Okay, so the easy stuff. Let's say that we didn't remove everything. Of course, we could just print out, we probably printed out above. Yeah, so we printed out right here. So we haven't removed all the students in this case. So now we're going to exit the program and our list is still going to have some students in it. So if we run with valgrind, right, we definitely have some memory leaks. And some of them are the students, which maybe were responsible for deleting, although that's, an argument could be made either way. But we're definitely responsible for the nodes. No one else has access to the nodes. So for certain, in my destructor, I want to make sure to delete all the nodes. Trying to remember, it's always a little current equals head, previous equals null pointer. I want to delete all the nodes. It's still the exact same traversal. Right down here, previous equals current, current equals current. Next, the difference is that, yeah, once I've done this, then I can delete the previous thing. All right, so that'll take care of the node, and then up here, I maybe think about deleting students. And, well, let's delete the students because I know that the main function's not going to do it. Again, this is not necessarily what you should do, but in this case, it'll work. So I'll just say delete current data. And that should clean up all of our memory, hopefully. Maybe it'll get a seg fault, I don't know. Let's just make sure it works. No seg faults. Let's see with valgrind. We did manage to clean up everything. So as we exited the list, the destructor got called, and in the destructor, I made sure, well, whatever's left in my list, I just deleted everything, just to make sure that nothing was left. Yeah.
Data allocated by once the destructor is called, it has no way to those pointers. You have to delete it outside.
Yeah. Well, I'd leave this. I would not do this probably ever, personally, because of there's a lot of reasons, right? But I leave this open to you guys because it is sort of simpler, like in your data structure, to just delete the data. And so if you're having trouble like with memory management, then go for it, right? Like that'll work. But you do have to be careful. Like for instance, a vector will never go through and do this, right? A vector, I have to delete everything, and maybe I do, right? I could always, in my main function, if I had like maybe I don't remove all the students, but I call get and I delete each one. I could do that. So maybe in my main function, I've figured out a way that I want to delete the students, but still on my list, I have to go through and delete the nodes. So yeah. Right, not to make things too complicated. You guys do whatever you like, whatever makes it simple, but yeah. I don't do this because, and in general, no libraries would do that. It's not, you don't want to take that, you don't want to make that assumption, right? So yeah. Other questions? All right, one question here. Why didn't we delete current? Yeah, that's a good question. So what happens here? Here we are. So if I want to advance current to next, and I want to delete this node. If I call delete, and then I call current equals current.next, I'm going to have a bit of a problem, right? So I need to advance my pointer before I delete the thing behind me. Otherwise, I can't advance the pointer. Right? If I do this and I call current or current.next at C++, so yeah, maybe it'll work. You should get a seg fault. In a perfect world, you would get a seg fault. But yeah. So in ours, we instead do this. We say current equals current.next, previous equals current equals current.next. Now that current is pointing to the next thing in the list, I can delete the thing behind it. And then I update these. And then I can delete this thing. And then I update them again. Right? And then I can delete this thing, and then we exit the list. All right. Other questions? Okay, so that is, yeah, and again, not to, yeah, at the end, so it is just a traversal. We use the same traversal. So once this points to null pointer, we're done, right? So here, the last time I do this, I update current equals current.next. At this point, current is equal to null pointer, but before I leave, I delete the last thing. And then I come up here and I'm done. I bump out of the while loop. And yeah. And you don't have to make this overly complicated if you don't want to, right? In your assignment 2, of course, you're not using linked lists, but you are using lists. And those lists will point to data, and maybe you want to delete the data in the list. If you want to do that, that's okay. As long as you don't have memory leaks, right? As long as you do it properly. So just give it a little bit of thought. Yeah. All right. Other questions? Okay. That is, I believe, all the linked list stuff. Now, there are variations that you will probably see. Oh, yeah, list cleanup. So in terms of memory, well, of course, all of the new nodes have to be deleted in the destructor. There's no one else that can delete them for us. Deleting data depends on the application. The default, right, if you look at the standard template library, they don't delete stored data because you never know what they're storing anyway, right? When we get to templates, this will make more sense. In this case, we do know we're storing student pointers, so yes, we can make the decision to delete them, and it can work out just fine. But in general, if I use a template, I don't even know that I'm storing pointers, right? I might be storing integers, or I might be storing objects, and so if I call delete on them, that's going to be a little bit tricky. I might get a seg fault or some weird delete error. Variants that we might see on assignment 3, so a doubly linked list. So that's always fun, but one of the things we can do with a doubly linked list is, well, now I can walk forwards and backwards, right? So I have a previous and a next pointer for each of my nodes, which means that I could start at the back and walk my way to the front, or I could start at the front and walk my way to the back. And then sometimes, instead of having a head and tail pointer, we have what's called a dummy node. So this node contains no actual data, but it acts as the head and the tail of my list. And it actually kind of makes some of these functions really elegant, actually. Although you do, if you take 2402, then you would have seen the ways that this really sort of eliminates a lot of the edge cases. It's kind of cool, but so we're not taking it explicitly. If I ask you for a doubly linked list, feel free to try it, or you can just use a head and a tail pointer. Index list, I didn't show how to do that. I think that would be very straightforward, right? If I ask you, get me the third thing in the list, well, you either return the third thing or null if there's no third thing. And a tail pointer, if I add a tail pointer, some of my lists, right? Well, if I want to add something to the back currently, I have to walk all the way from the front to the back. But if I have a tail pointer, I can just kind of, I can say, well, make me a new thing, point the tail at it, and then point my tail at the new thing. But yeah, so those are some of the things you might see for assignment 3. But yeah. All right, so that brings us to inheritance. So we're going to continue talking about basically encapsulation and memory management, but now it's complicated by this fact that, I'm going to inherit characteristics from my parent class, and what exactly does that mean in terms of like memory management, right? And encapsulation. So we're going to look at all those things. We're going to look at the memory layout, or the typical memory layout, right? So C++ is not, it's a language, yes, but a language is just a specification, which means that some of these things, yes, you have to do it this way, but other things you have choices in. So when we say memory layout, yes, our compiler uses this memory layout. I'm not sure if this is actually dictated in the C++ specification or whether it's left up to the implementer to figure it out. But so all that is to say that occasionally we tell like little lies, right? They're useful lies. I give you a model and probably your compiler implements it, but it's possible that it doesn't. We're going to talk about memory access, constructors and destructors, inherited functions, and then different types of inheritance. So in C++, of course, things can be very complicated. I can inherit privately or publicly, and I can actually have multiple parent classes. So yeah, role of inheritance in object-oriented design, another method of abstraction and encapsulation, sure. Classes are a more detailed specification. We're talking about an ISA relationship, right? This helps us reuse existing code. And in C++, we often talk about the base class and the derived class, right? You might also talk about parent class and child class. So in this case, let's say I have a boat, and a boat is sort of a general class, right? It's something that floats on the water, has maybe a way to move across the water and carry passengers. And then I can specify some more specific type of a boat, a sailboat, where I add some more features that are, sort of exclusive to that specific type of thing. Yeah, I'm going to look at it today. Today is really busy. I'm not sure what happened. I thought Lars was going to, we had a few that didn't get marked for some reason, and Lars was going to track it down, but I didn't really, I'm not sure what happened with that, so I'm going to have to, I'll talk to him today. All right. So, well, one of the things we're going to, we're kind of peering under the hood here in C++. So what happens at a low level when I inherit from a class boat into a class sailboat? And really, actually, it looks a lot like composition, right? So you may hear things like prefer composition over inheritance. And I suppose that's a decent rule of thumb. It really depends on your domain. Inheritance can be quite useful, right? Like if you use a game engine, you're using inheritance, right? You have a game object, you inherit from it. You get a lot of code for free that way, and then you just implement like the last little bit that sort of decides how your game behaves. Right? So inheritance works really well in some domains. It can also be very brittle. We'll talk a little bit about some of the pitfalls. But if I look at how it's represented in memory, well, I have my class boat, which is basically a struct that stores one int, which is the capacity. And then somewhere off in the code segment is this function ready to take, a boat and a direction as arguments. If I then make a derived class of boat called sailboat, and I add a couple more member variables, well then now I have a piece of memory that looks like this, right? So it's a class sailboat that has a base class of boat, but when I get down to what is actually contained, it's the same three variables. Okay, so one way to think about inheritance, we say prefer composition over inheritance. Well, they're kind of the same thing almost, right? I mean, compiler is going to do some additional checking about, so that I can pass in a sailboat into a function that would accept a boat. But when it comes down to memory, it really is just like composition. It's as if I made two structs, and then inside my sailboat struct, I put a boat struct. All right, so that's going to be a useful model to begin with, right? When we talk about single inheritance and like how do we solve these problems of encapsulation? Well, basically, if you look at the solution for composition, the inheritance solution looks almost the same. Okay, so this is going to be a good way to think about it. When you get to multiple inheritance, this kind of breaks down, right? Because now you need a table to figure out where everything is. But it will be useful in the beginning. So, the one thing about we've been emphasizing is member access and encapsulation, and that still applies here, right? So I have a boat, and my sailboat inherits from boat, but this capacity is still private to my boat class. So as a sailboat, how do I handle that, right? So how do I do things like initialize my capacity variable? But all right. Sure. Okay. So we have here an animal class, right? And nothing too complicated. It has a name, it has an age, and it has a lifespan. Name and age are private member variables. The lifespan is protected, right? So when we inherit, if we use the protected access modifier, that gives my derived classes access to that particular member variable. But otherwise, let's make an animal. We'll print out the animal, and then we will take it from there. We'll start making chickens. Oops, I opened the wrong one. It's like that is the normal course of the normal path of any piece of software. It seems like it starts off really lightweight and beautiful and extensible. You just put the things in you want, and then at the end, everything's vying for space on my. I just want to see my code, man. Anyway, print the animals. Oh yeah. Okay, so I have an animal. We can see when the animal is constructed. We print the animal. Animal's named Alex, age 8, lifespan 12, and then the animal is destroyed. And of course, this is a very general class. There's nothing specific here about what type of animal. So we're going to use inheritance to define that. We're going to make a chicken to start with. So of course, my chicken class, I will need to know about the animal. header. So the header contains enough information to define it. Chicken. And then public animal. So I'm going to publicly inherit from the animal class. Okay. This is important. If you leave it out, it's by default private on a class, and then you will get behavior you don't really expect to get. So this public inheritance. All right. So, well, so what problems do we have? Well, we have the same problems we have in decomposition. I have an animal now, and I need to initialize it, right? So there's a bunch of member variables in here that I want to initialize. Well, of course, we want our initialization to be done within a constructor, and our constructor, we're going to take in all the information we need to initialize both chicken and animal. Now, our chickens will lay a certain number of eggs per day, so this is the more specific thing that we have to worry about, but animals in general need a name. Animals need an age. Animals need a lifespan. And a chicken needs an egg count. I really want to, I might just, for the sake of simplicity, cheat a little bit here and put all of this in my header file. The ints and floats as reference. So no, we don't have to. So we pass this by reference. So passing by value will work because I don't want to modify any of these values. I pass the string by reference because, well, rather than making a copy of this, maybe a very long string, I just pass in a memory location and then I can do whatever I like with it. But here, right, so this is, by passing by reference here, I'm saving on the amount of things that I'm copying. I'm copying 8 bytes instead of however many bytes this name string is. But this is actually only 4 bytes. And so if I pass by reference or pass by value, I'm copying about the same amount of stuff. So this is not really, if I pass this by reference, it's not saving me anything. It's actually slightly longer, although in practice it's probably all about the same. So in terms, when I pass primitives, I can pass by value unless I want them to use them as an output parameter. Okay, so really only objects and, well, strings we consider, we sort of, they straddle the line between object and primitive, but you know, they can be quite big, so we want to pass them by reference. But yeah, hopefully that answers your question. Any other questions? Okay, so let's make a chicken. Well, already, if I look at my animal class, oh yeah, let's actually see out. Let's see when this chicken is made, and let's also see when this chicken is destroyed. We'll get into things like initializing. We've got a bunch of problems to solve. But first, let's see what happens if let's get rid of this animal stuff and let's bring in a chicken. And call print, right? And you can see the compiler's happy with that because well, we talked about how we can treat inheritance like composition in terms of the data, which is true. In terms of the functions, though, like I get actually also to inherit the functions, right? So my chicken now has a print function, even though I don't explicitly have one. So I can print out my chicken. And so printing my animal's named Al, age 0 with lifespan 0. If I look at, well, I have a bunch of default values. So the default constructor got called. But more to the point, if I look at the order that these constructors were called, well, my animal constructor got called first, and then my chicken constructor. And then when they're being destroyed, that happened in the opposite order. And this is the exact same pattern we get with composition, right? If I had instead of inherited from animal, I could have done something like this. Well, it's not going to like this print statement, but I'm just going to put a print just for fun. Well, we get the exact same thing, right? So this is, when I said treat it like composition, it solves a lot of our problems. Like, so what gets made first? Well, the animal part gets made first, and I can think of it as either I'm inheriting from animal or it's containing an animal. Both of those sort of work out to be the same. Okay. All right. Well, we want to actually also print. And what we want, actually, we want to print the animal stuff. And if I had an animal, you know, member variable, I would do something like this. Because I don't have access to these private member variables necessarily, so I can't actually print things out the way I want to. So I'm going to rely on the animal class to do this for me. I don't actually have a member variable called al. That is an animal. I inherit from animal, but I can still do the same basic thing. I can just say, well, it doesn't really have an explicit name other than animal class, but there is a part of my chicken that is an animal, and please call the print function on that part. Okay, so I'm going to use the scope resolution operator here to sort of mimic the thing I would do with composition, which is just call the print function on my animal part. And then I would say, who is a chicken who lays eggs per day. Okay. All right, so when I use inheritance, I think of it as, well, my chicken has now an animal part. That animal part gets constructed first. And if I want to, let's say in this case, I'm overriding a function. And if I want to call the parent function or the animal part function, I can just use the scope resolution operator. Okay, so this is how we solve this encapsulation problem where some of these member variables are private and I don't necessarily have access to them. Yeah, I was just demonstrating that basically at this stage of the game, it's very similar, right? It's not the same because I don't inherit the functions if I use composition, but I do get all the same sort of like problems. And when I look under the hood at what's happening in memory, inheritance, at least at this level, is composition. Just with some fancy the compiler does a little bit of checking for us, but otherwise it's very, very similar. So, and the point of all that is that, well, when you have these problems, you can just think of them as like composition and then solve them in the same way. All right, questions? All right. So we have a chicken. The animal part was constructed first. I want to initialize all of these, so I might do something like egg count equals egg count. Of course, if I try and do something like this is inaccessible. It's part of my animal class we can see here, and it's private. But my lifespan is protected. And so I'm allowed to do this. So I can't initialize my name directly, but I can initialize the lifespan if I wanted to. And down here in my print function, I could utilize lifespan as if it was my own. So this should actually initialize part of my animal class. So Al, my name is still Al because I haven't been able to change that yet, but my lifespan is now 10. And I'm also a chicken who can lay 5 eggs per day. Age and name are still private, so I have not been able to access them yet. But yeah, questions? All right. Well, the solution to how do I initialize name and age is the same as I did for composition in that, well, I want to call the constructor on this animal part. But I want to do it, right? If I look at the order that it's constructed in, my animal part is constructed first, and then my chicken part. So I have the same problem I had with composition in that I want to grab that animal and initialize it before my chicken constructor. And well, I'm just going to call that constructor using, this is a base class initializer syntax, which is the same as member initializer syntax, right? I'm just grabbing this animal part and giving arguments to the constructor before my chicken part constructor gets called. So now I don't need to do this, right? I could do that, but well, the animal constructor knows best how to initialize all these member variables, even the protected ones. So I kind of want to rely on it to do that. Maybe it has some fancy checking that it does behind the scenes. I don't want to interfere with that. In my chicken constructor, I'm going to stick with initializing chicken parts. So now I should have sort of a fully fledged animal. So now, yes, I have a proper name, Chicky, and I have an age of 5, and basically all my member variables are initialized. I'm able to print myself, but again, I can't, even though I'm inheriting from this, there's still these rules for access, right? I cannot print my animal outside of the print function because I can't access things like age and name. And when I initialize it, well, I probably want to rely on that animal constructor rather than my own. Okay. Questions? All right. So in C++, constructors, especially with inheritance, are important because every one of them in your inheritance hierarchy is going to get called. All right. So we do have to, I mean, it's good practice to always supply arguments to your parent constructor and not rely on roundabout ways to initialize member variables. All right. So yeah, all my base class members are inherited, all data members, all member functions, right? So I was able to call that print function on my chicken before I implemented it because I just used the animal print function. But I was also able to override it and provide my own and then just rely on my animal print to print out the animal parts. Public and protected base class members are accessible to the derived class. We saw how the protected member was. We didn't see any public members, but other than the print function. Private members are still included, right? Age and name are still there in my chicken, but I cannot access them directly. I have to rely on whatever the animal, right? I have to rely on whatever their public interface is. That's the only thing I have access to. Well, public and protected, right? So private things are still private, even when I inherit. All right. Right. And of course, even though I'm inheriting, right, I can still be a friend to my base class or child class if I wanted to. Right, here I am overloading or overriding the print function, and if I still want to call on my base class behavior, I can do that. I just use the scope resolution operator. The nice thing about this is I can go as far up the hierarchy as I want, right? Maybe I have like an organism that is a parent class to animal, and I can call organism print if I want to. So all of those are open to me. So in terms of member access, I have a base class object that has private, protected, and public members. And if I look in my derived class, well, the private members are invisible. And this is basically the same as composition, right? I'm not allowed to access the things that the member variables the private parts of the member variables. Those are still private. But I do have this new protected option, which means that, it's private from everyone else, but the inherited objects get access to them. And then public members are still public. And then in my derived class, I can allocate private, protected, and public as well. Ooh. Just thinking I forgot to do the woo clap for the linked list. So we'll finish up just this part here, and then we'll do the woo clap, and then we'll come back to this. Of course, this model extends even further, right? So my private thing in my base class becomes invisible to my derived class. That stays invisible. Protected stays protected if I have two layers of inheritance. Public stays public. But my new private, of course, becomes invisible to my derived class. Protected stays protected, public stays public, and then I can allocate new members with whatever access modifiers I like. Yeah, so public and protected I can access directly. Private members, well, I have to rely on the interface, right? So maybe there's a getter or setter I can use, or just functions. If I want to initialize them, I should call on the base class constructor, etc. The order of invocation of the constructors. All right, this is important. This is also an easy test question, right? But if I have an inheritance hierarchy like this, then my objects are built from the top down. So the vehicle would be constructed first, and then the car part, and then the Mazda part, if I was making a Mazda object. All right. And so, in my Mazda constructor, I would use the base class initializer syntax to call the car constructor. And in my car constructor, I would use the same syntax to call the vehicle constructor, right? And then I could initialize things properly all the way up the hierarchy. And they are actually destroyed in the reverse order, right? So if I have a Mazda, then the Mazda part gets destroyed first, and then the car part, and then the vehicle part. And this is similar again to composition, right? So the container gets destroyed before the containee, and you could think of the vehicle as being contained in car, and car being contained in Mazda. Yeah. All right. So that's constructors and destructors, order of operations. Let's take a jump over to the to the woo clap. Do the linked list woo clap. Now, it's not very long, but it's a little review. Okay, so I shrunk my screen a little bit because some of this code wasn't fitting, but given a singly linked list, which of these is the correct implementation of add front, right? So again, I have a node. The node has a constructor exactly as we saw in our code. I'm trying to add a student pointer to my linked list, but I want to add it to the front, right? So I have a specific function that just does that. And so yeah, which of these would work? So, and also, what does it mean to add to the front? What are the special considerations that I have to do? Right, if I have the head is pointing to the front, and I want to, whatever, there's some more data perhaps. B and C, and I want to add A to the front. Well, what do I have to do? Well, I have to redirect a couple pointers, right? So I want A to point to B as the next thing in the list, and I guess I don't have an eraser. I want head to point to A. And then you might consider, well, what happens if my list is empty? But maybe you get that for free, right? Maybe we get a little more functionality. If we just consider this case, maybe it elegantly extends to the empty list case. But let's see. So head equals new node, head equals head next. I mean, we made a new node, that's good. Head equals head next. That's not quite what we want. We want the head to point to the new node. So node next equals head, head equals node. This looks like a pretty good candidate, right? That's what we wanted. We wanted A to point to B, and then we wanted head to point to A. And so that might be good. We could take a look at some other stuff. This one definitely not. Head next equals node. We're going to, well, this is going to cause problems. We're going to actually detach our list, and we will have a list that consists only of A afterwards. I'm going with 2. Let's go with 2. It looks like 2 is correct. This one, head is not equal to null pointer. Yeah, I can't see all the code. I guess this might, I mean, judging by what I'm looking at, this could work. Head is not equal to null pointer. Right. Is there anything else hidden there? I don't. Okay, so this would work too then, right? Yeah. All right. It's just not strictly necessary. Oops. So, same thing. I want to remove something from the front. Which of these would do the trick? Let me see if I can get rid of this stuff. Again, it's yeah. You have to think carefully. So I want to remove the first thing, and I'm just going to start with thinking about, I'm not going to worry about what if head is equal to null pointer, but just this. Well, I want to say head equals head not next. I definitely want to do this, but I want to remember to delete this, and I also have a piece of data. I'm going to return this. Okay, so like this line here is pretty good. This would actually work, except I have a memory leak, right? I never actually delete the original. I never delete the thing that the first node in the list. This looks pretty good, I think. Goner equals head.data, node.temp equals head, head equals head next, delete temp, return goner. I can't see if there's anything additionally there. This one, temp equals temp next, delete temp. I mean, I'm deleting the second thing in the list here. That's probably going to cause me a lot of issues. Here, I'm just deleting the head and returning goner. Again, that's going to cause problems. So it looks like number 2. Yeah, and it looks like most of you got that right. All right, questions? Okay. Get last. So it's a linked list, and I don't have a tail pointer, at least in this implementation. In the implementation we looked at, if I had a tail pointer, it'd be, of course, very easy. But here I have to walk to the back of the list, right? So I need some sort of traversal. That's not really a good idea to use the head as my temporary pointer to walk through the list, because now I'm going to everything I walked past, I'm never going to be able to see again. So definitely not 1. current equals current dot next. So in this case, I'm going to keep walking until current is equal to null pointer, and then I'm going to try to return current data, which is going to give me a seg fault. So while close, this is not quite what I'm looking for. I want something like this. So in this line, I'm going to check, well, the next thing is not a null pointer. I'm going to keep advancing, but if the next thing is a null pointer, then the current thing is the last thing in the list, right? So I want to return that. I think I'm making an assumption here that there is at least one thing in the list, because I didn't do an explicit check on whether or not head was equal to a null pointer. But yeah, so I guess there's technically no correct answer, but there is a best answer, which would be number 3. All right, questions? Okay. That's it. All right. Okay. So back to constructors and destructors. So we've talked a lot about how inheritance looks a lot like composition. Well, what happens if we have inheritance and composition? Well, now the order that things are constructed and destructed are as follows. I look at my base class, and anything that is contained in the base class gets constructed first, and then the base class constructor gets called. And then in my derived class, it's the same thing, right? So if I contain some object, that gets constructed first, followed by the derived class. Let's take a quick look at a quick example. Yes, all right. So I have an animal, the same animal class I had before. I had a chicken, same chicken class. Now I'm going to add an egg class, and the egg class doesn't do much other than, I'm going to store a string that describes the egg in some way. So in my main function, I make a chicken. And for now, I just have an animal and a chicken part. So the animal part is made first, and then the chicken part. Yeah, everything's working fine. So I'm going to add an egg to the mix. Right, and then in my print function, that can produce something. Egg.get size. All right. So now, yeah, this chicken object statically allocated. And yeah, I'm a chicken that can produce 10 mini eggs daily. The animal is constructed first, and then the chicken is constructed. But inside the chicken, my egg gets constructed first, and then the chicken part. As I'm exiting the function, the chicken, it's everything in reverse order, right? So chicken gets destroyed first, then the egg is destroyed, and then my base class, the animal, is destroyed. And if the animal had some sort of contained object, it would be the same thing. That contained object would get created first, and then destroyed last. So yeah, that's a quick little addition to our constructor talk, but any questions? Okay. So yeah, this is sort of, I did things a little bit out of order, but right, just a reminder of how we initialize things in our base class is, well, we never want to override a constructor in C++. Well, we can't, right? So every class in the hierarchy, their constructor gets called, and we want those constructors to have all of the proper data to initialize their parts. We never want to take control of like initializing animal parts in a chicken class. We want to keep encapsulation because then we can make changes to the base class, right? So it's still important to do that. But yeah, of course, the solution, as we saw, is to use the base class initializer syntax. Okay, so we've talked about member variables. We're going to talk about a little bit about member functions. So of course, we inherit all of the member functions of our parent class. The private ones we cannot access, but the public ones and the protected ones we can. But maybe sometimes I want to redefine some of these functions. That's called function overriding. Yes. Not to be confused with function overloading, which I do all the time. But yeah, let's take a look at the example. So my animal class is a little more complex now. Now they forage for food, and there's two actual forage functions, right? So I'm using function overloading here. So one takes an integer and the other takes a float, and they can both exist with the same name in C++, right? You can't do this in C, but C++ allows you to do that because the compiler can tell them apart based on the arguments. So in my chicken class, I do not actually override these functions yet. So that means I inherit them. So I have an animal, Al, and a chickie the chicken. So Al forages, and then I could do the same thing with my chicken. Can forage for 10 minutes or for half an hour. Right, chicken's very hungry. This has to be a float. Okay. So I inherit those. I do not define them in my chicken class. Oh, did I? I think I left in this. Okay. All right, so I have an animal Al, age 8, and basically at feeding time, Al can forage for 20 minutes, and the chicken can, do the same thing. I can forage one of two ways based on the functions that I inherited. Yeah, so good question. What if I don't put this here? This is by default a double, right? The double precision float. So a float, if I'm not mistaken, is 4 bytes. Is that right? Yeah, that's right. Okay, so a double precision float is 8 bytes. That's all. So yeah, if you're using floats, so normally, I think we're not so memory constrained as we once were. So like using doubles is, pretty standard, I think, in a lot of contexts. But still, if you're working in OpenGL or something and you need a float, you got to say that this is a float with the F. Yeah. Other questions? All right. Okay, well, let's say now my chicken, so there's some weird behavior coming up. Let's say I want my chicken to have its own forage function, right? So, and it's going to take, instead of a amount of time, it's going to take a food type as a string. And so then here I will implement my forage function and say, chicken will hunt for this food type. What did I do? Oh yeah, it should be const. This actually creates a problem. So, and right away you can see here now the compiler, once upon a time, the compiler was happy with these function calls, now no longer. Right, so it says no suitable constructor exists to convert from an int to a string. Not really a helpful error message, but what it's trying to do is it's saying, well, the only forage function I recognize here is the string one. So although before I inherited these, now they're no longer visible, at least calling them in this way. So really the only thing I can do is have my chicken forage for worms. And for now, well, let's just make sure that that works. So my animal will forage for 20 minutes and my chicken will forage for worms. And yeah, so Al forages for 20 minutes. Chicky the chicken will hunt for worms. So kind of strange behavior, I don't know, but if you override a function, you lose access to any overloaded functions, right? So these still exist. I could still call them on the animal class, but they're now invisible here. I'm not sure exactly why, but of course, like everything in C++, there's a way to fix this. I could say, well, I don't want to call this forage function with the string. I want to call the forage function with the int, and you're going to find that actually in the animal class. All right, so I can use the scope resolution operator to say that, well, the functions you are looking for are not in my chicken class, they're in my animal class. And so now, if I override a function and I want to use the old functions, I have to explicitly say where to find them. But they still will work. All right, so yeah, questions? All right. Sort of strange. I'm not sure exactly the reason. I'm sure there's some deep technical explanation as to why that is preferred. Yeah, so this is just an explanation of all the things we talked about. Basically, if I overload a function in my child class that from my base class in my child class, then in order to call the base class function, I have to explicitly use the scope resolution operator. All right. I think we'll stop there for today. Next class we'll continue talking about inheritance and overloading and overriding. Well, you'll often hear me use them incorrectly, but overloading means that a function that exists in my base class, I'm going to redefine in my child class, and that's overriding. Overloading is where I have two functions with the same name but different parameters. Yeah. 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 So that's any more questions or okay. Yeah.
So